This is a tutorial to understand a continuous probability distribution. And specifically, in this case, we're interested in the random variable x, which counts the time to failure in years for a particular component. Now, in this case, it's a continuous variable because it's measured in years, which is easily divisible, and fractional values make sense. In this case, let's consider that we have the following observations. So from the last 10 parts that failed, they lasted the following number of years: 0.89, 1.12, 0.96, 0.89, 0.74, 1.02, 0.76, 1.49, 1.82, and finally 0.70. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. Now in this problem, we want to develop a cumulative distribution function for this observed random variable. However, the first thing that's probably useful to do is to sort these in ascending order. So the sorted order looks to be, well, the smallest one is 0.7, then 0.4 or 0.74, then 0.76, then it's like 2 copies of 0.89, then there's a 0.96, 1.02, 1.12, 1.49, and finally 1.82. Now remember in these cases that the cumulative distribution function, f of x, is the probability that x is smaller than or equal to some particular value. So based on these observations alone, we can start developing some observations. So for example, the probability that, well, let's actually, we'll erase this piece here to give us some room. So the probability of there being something, let's see, I'll just write this again. Probability that random variable x is less than or equal to some particular value x. So let's take a look at these examples. So here, if we have one observation at 0.7, the probability that x takes on a value less than or equal to 0.7 is 1 out of the 10 observations. So anything less than 0.7, it would be 0. We'll just kind of sneak that in there. Then up until the point where we observe this 0.74, we then know that 2 out of the 10 observations were less than or equal to 0.74 or 0.2 or 20%. When we reach the point 0.76, we know they're 30% or less than or equal to 0.76. For 0.89, since there's a duplicate of the same copy, we know that actually 50% were less than or equal to 0.89. So 10% for this one, 10% for this one, but we add them together. So we know 50% of the data, 50% of the observations were less than or equal to 0.89. Here, we can continue the trend. 60% were less than or equal to 0.96, 70% were less than 1.02, 80% were less than 1.12, 90% were less than 1.49, and 100% were less than or equal to 1.82. So if we were to plot this cumulative distribution function, for example, we could plot x versus f of x. Cumulative distribution functions always start at 0 and end at 1. And just to make things easy, I'll do 0.2, 4, 6, 8. It's not that equal, but close enough. 0.2, 4, 6, 8. So we know that anything less than x equals, so our x also range is about 1.0 and about 2.0. So anything less than about 0.7, we didn't see any data. So the probability that the random variable takes on one of those values is 0. And at our first observation, 0.7, our smallest observation, our probability jumps up to 10% or 0.1. And it stays there until our next observation, which is 0.74, when it rises up to 20%. And then at our third observation at 0.76, it jumps up to 0.3. And at our next observation at 0.89, it jumps up to 0.5. So here, this is about 0.89, jumps up to 0.5. And at our next observation, 0.96, it goes up to 0.6. And then at just over 1, it reaches 0.7. And then at 1.12, it jumps up to 0.8. And then finally, our last data is at 1.49, about halfway between 1 and 2, it jumps up to 0.9. And then our last data is at 1.82, let's say it's about here, where it jumps up to 1. And it stays at 1 for anything bigger than that. So here's our cumulative distribution function found from our data, from our observations. We can see that it's a discrete plot because we only have a finite number of observations, but it does, in this case, follow a general curve. Now, in this case, we may have a theoretical distribution to model the existence of time to failure. And specifically, the one that probably makes the most sense is a Weibull distribution. So a Weibull distribution has a PDF expressed with the equation f of x is k over lambda times x over lambda to the power k minus 1 times e to the negative x over lambda to the k power, where here k is something called a shape factor and lambda is a scale factor. So in our particular case, we could make certain assumptions here. So maybe saying that k is 2 and lambda equals 1, just to simplify this problem, to give a corresponding PDF equation of 2 times x to the k minus 1 times e to the negative, 2x times e to the negative x, since x squared. All right, so this could be our theoretical PDF. And in this case, a Weibull function also has a well-known cumulative distribution function, big F of x. If we look it up in a reference, the form of the cumulative distribution function is 1 minus e to the negative x over lambda to the k power, which in our case with these assumed constants is 1 minus e to the negative x squared. And we can see very clearly that just as a side, the derivative of the cumulative distribution function is the PDF. So the derivative of 1 minus e to the negative x squared, if you remember back to your high school calculus or your college calculus, does indeed yield this particular value. So for this cumulative distribution function, we may want to evaluate it at certain x values. So I can just build a table here based on what I've calculated from a calculator. So f of 0 is 0, so that's clear. F of 0.5, so this is again measuring the probability of having something less than or equal to half a year before failure is 0.15 or 15%. F of 1 year, the probability of failure happening less than 1 year is 0.4. F of 1.5 is 6.6, 60%, and I'll just go up to 2 in this case. F of 2 is 0.75. Again, these are using this equation, so evaluating it in a calculator. And again, the meaning of this is the probability that the random variable x, which is the time to failure in years, is less than or equal to some particular value, so in this case, like 2. So the probability that the time to failure is less than or equal to 2 years is 75%. So we could take this theoretical distribution and plot it on the same axes. We could use these ones if we want, or we could draw new axes. So f of x ranges between 0 and 1, and in this case, our x goes between 0 and 2. And we could plot these individual values, so 0, 0, 1.5, 0.15, 1.4, 1.5, and 0.6, and 2.75. And since this is a theoretical distribution and it has essentially infinite observations, we can connect these points with a continuous line. And if you're using a plotting package, for example, in Python, we could evaluate this CDF equation, which is right here, evaluate it at a lot of x points from 0 all the way up to maybe a larger number, and visualize the curve, which again ranges between 0 and at the extreme value. I just want to add one more item to this problem. So if we wanted to write our cumulative distribution as an equation, we can use a similar approach as the discrete case and describe it as a series of cases. And in this case, we could say, for example, that the cumulative distribution function value, I'm just going to make a little bit of room here, is 0 if x is less than 0.7. It's 0.1 if x is between 0.7 and 0.74. This should be 0.74. It's 0.2 if x is between 0.74 and 0.76. It's 0.3 for x between 0.76 and 0.89. And it's 0.5 for x between 0.89 and 0.96. And it's 0.6 between 0.96 and 1.02. It's 0.7 between 1.02 and 1.12. 0.8 between 1.12 and 1.49. 0.9 between 1.49 and 1.82, and finally 1.0 if x is anything bigger than 1.82, which was our last observation. So this form of our cumulative distribution function corresponds exactly to this plot that we've shown, and that's one way of representing a continuous distribution CDF.